On July 16, 2024, a fireball tore across the sky above the northeastern United States. People heard a sonic boom. Cameras captured the object racing through the atmosphere. Then one fragment completed an extraordinary journey by crashing through the roof of a house in Hillsborough, New Jersey. At first, it looked like an expensive accident caused by a black rock from space. 2 years later, scientists revealed that the meteorite carried something far more valuable than anyone expected. Hidden inside it were signs of ancient salty water, organic compounds, and amino acids preserved from the early solar system. The rock may contain a chemical record of the environment that helped provide young planets with some of the ingredients needed for life. The meteorite is now known as the Hillsborough meteorite. It belongs to a rare group called carbonaceous chondrites. Unlike many meteorites made mostly from metal or relatively dry rock, carbonaceous chondrites contain carbon-rich material, water-altered minerals, and complex organic chemistry. They are among the most primitive objects scientists can study because their ingredients formed during the earliest history of the solar system. Most meteorites are discovered long after they land. They may sit in deserts, fields, or ice for years before someone recognizes them. During that time, rain, soil, bacteria, and human handling can contaminate their chemistry. That creates a serious problem when researchers are looking for water or organic molecules. They must determine whether those materials came from space or entered the rock after it reached Earth. Hillsborough was different. The fall was observed, its path was recorded, and the surviving fragment was recovered almost immediately. The homeowner handled the broken pieces carefully and stored them in glass containers. This greatly reduced contamination and gave scientists an unusually pristine sample of a primitive asteroid. Researchers combined public videos, security camera recordings, weather radar data, and other observations to reconstruct the object's path. Before entering the atmosphere, the original rock may have weighed around 50 kilograms. Most of it burned or broke apart during the descent, leaving only a much smaller fragment to reach the house. The reconstructed orbit pointed back toward the main asteroid belt between Mars and Jupiter. That region contains remnants from the era when planets were forming. Some asteroids have remained chemically primitive for billions of years, preserving materials that existed before Earth became a mature planet. Laboratory analysis classified Hillsborough as a CM12 carbonaceous chondrite. The letters refer to a family of meteorites that experienced reactions involving liquid water inside their parent asteroids. The numbers describe the degree to which their original minerals were chemically altered. The asteroid was not necessarily covered by oceans. Instead, ice inside the body may have melted after radioactive elements warmed the interior. Liquid water then moved through pores and fractures in the rock, reacting with minerals and changing them into new compounds. Over time, the water became increasingly salty as it dissolved material around it. Inside Hillsborough, researchers found an unusual chemical record of these ancient brines. The meteorite contained high concentrations of salts and minerals formed through water-rock reactions. Its chemistry suggested that liquid water once existed inside its parent asteroid under conditions that were different from those recorded in most previously studied CM meteorites. This matters because water did more than make the asteroid wet. It transformed its chemistry. When liquid water reacts with minerals, it can create clays, carbonates, salts, and other hydrated compounds. It can also move carbon-bearing molecules through the rock and bring different substances together. An asteroid containing heat, water, minerals, and organic material becomes a natural chemical reactor operating over thousands or millions of years. Scientists found a wide range of organic compounds in the meteorite, including amino acids. Amino acids are best known as the building blocks used by life to construct proteins. Finding them in a meteorite does not mean the asteroid contained living organisms. Amino acids can form through non-biological reactions in space and inside asteroids. Their presence is still important because it demonstrates that some components used by biology can be produced before planets form life. Meteorites could then deliver those molecules to the surfaces of young worlds. Researchers also studied the balance between different versions of amino acid molecules. Many amino acids can exist in two mirror image forms, often described as left-handed and right-handed. Life on Earth overwhelmingly uses one orientation when building proteins, even though non-biological chemistry often creates both forms in similar quantities. The Hillsborough sample contained a mixture consistent with extraterrestrial chemistry rather than obvious contamination from terrestrial life. Some compounds were uncommon on Earth or occurred in patterns that strengthened the conclusion that they formed in space. The meteorite also contained complex organometallic compounds, in which carbon-based molecules interact with metal atoms. Similar categories of chemistry are important in modern biology. Metals sit at the centers of molecules involved in processes such as oxygen transport and photosynthesis. The compounds in the meteorite were not living biological machinery, but they show that surprisingly sophisticated combinations of carbon and metals were possible inside primitive asteroids. Together, the water-related minerals, salts, amino acids, and organic compounds create a picture of an active chemical environment. The parent asteroid began as a collection of dust, rock, ice, and carbon-rich matter. Internal warming melted some of the ice. The resulting brines flowed through the body, altering minerals and allowing new chemistry to develop. Eventually, collisions shattered the parent asteroid. One fragment entered an orbit that slowly changed through gravitational encounters and other forces. After billions of years, it crossed Earth's path, burned through the atmosphere, and landed inside a New Jersey home. The study does not prove that meteorites created life on Earth. The origin of life remains unresolved, and no single delivery of organic material can explain the transition from chemistry to biology. Life requires far more than a collection of amino acids. It requires systems capable of storing information, using energy, reproducing, and evolving. However, the meteorite supports the idea that early Earth did not have to manufacture every useful molecule from nothing. Asteroids and comets repeatedly struck the young planet. Each impact could have delivered water, carbon-rich compounds, and prebiotic molecules. Rather than being empty rocks, some of these objects may have arrived as packages of chemically processed material. The distinction is important. If useful organic chemistry begins inside asteroids, then the early stages of life story may be distributed across an entire planetary system. A planet could receive ingredients that had already spent millions of years reacting inside smaller bodies. This possibility extends beyond Earth. Carbonaceous asteroids are not unique to our solar system in principle. Dust, ice, metals, and organic molecules appear in planet-forming environments across the galaxy. If water-rich asteroids commonly develop complex chemistry, then the ingredients associated with life may be produced around many stars. That does not mean life is common. It means some of the raw materials may be. Hillsborough is also valuable because it can be compared with samples returned directly from asteroids. Japan's Hayabusa 2 mission brought material from Ryugu back to Earth, while NASA's OSIRIS-REx mission returned samples from Bennu. Those missions protected their cargo from Earth's atmosphere and environment, creating exceptionally clean collections. Meteorites offer something different. They fall naturally and can provide larger or more diverse samples, but contamination is usually a concern. Because Hillsborough was recovered so quickly, it creates a rare bridge between ordinary meteorite studies and controlled sample return missions. Its chemical similarities to primitive asteroids such as Bennu and Ryugu may help scientists interpret the histories of those worlds. Differences are just as useful. Hillsborough's unusual salt-rich chemistry suggests that water inside primitive asteroids did not always behave the same way. Some bodies may have contained relatively fresh water, while others developed concentrated brines through evaporation, freezing, or extended reactions with rock. Researchers may be able to use these chemical patterns to reconstruct where water moved, how long it remained liquid, and how temperature changed inside the parent body. That turns a small meteorite into a geological map of an asteroid that may no longer exist. The rock also demonstrates why rapid recovery matters. Networks of cameras and radar systems can track fireballs, while reports from the public can help researchers locate fragments quickly. Every hour that a meteorite remains exposed to rain, soil, or careless handling can erase part of its original chemical record. In this case, a homeowner's decision to preserve the fragments carefully protected material that had survived for billions of years. The meteorite is now being curated so that future researchers can study it with techniques that may not yet exist. The most dramatic part of the story is that the meteorite arrived without a spacecraft. No probe traveled millions of kilometers to collect it. A piece of an ancient water-rich asteroid simply entered Earth's atmosphere and delivered itself through a roof. Inside that rock was a record of liquid water flowing through an asteroid before Earth became the world we know today. There were salts left behind by ancient brines, organic compounds produced without life, and amino acids that biology would later use in every living organism on this planet. The Hillsborough meteorite does not reveal exactly how life began, but it shows that the chemistry leading toward life may have started far away from Earth, inside dark asteroids moving through the young solar system. A stone that looked like debris from an accident may actually be a surviving fragment of a much larger story. Long before oceans covered Earth, water and organic chemistry were already interacting inside small worlds. Billions of years later, one of those worlds sent us a sample.